Almost 150 years before actual atomic theory was established, Boyle, Newton, Bernoulli, and several other scientists tried to explain the behavior of gases. They considered that gases are made up of tiny atomic particles. Later in the 19th century, Maxwell, Boltzmann, and others successfully developed kinetic theory. Kinetic theory explains the behavior of gases based on the idea that gas consists of atoms or molecules which are in constant random motion. Kinetic theory has widespread applications. This theory leads to the molecular interpretation of pressure and temperature of a gas. It is also consistent with gas laws like Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's hypothesis. Kinetic theory helps explain the specific heat capacities of many monoatomic, diatomic, and polyatomic gases. It relates the measurable properties of gases like viscosity, conduction, diffusion to the size of molecules. In fact, these relationships help in the estimation of molecular sizes and masses. The atomic hypothesis is one of the most important theories ever proposed. What is the atomic hypothesis? According to the atomic hypothesis, all things are made up of tiny particles called atoms. These tiny particles move around in continuous or constant motion. Atoms attract each other when they are separated by small distances, and repel each other when compressed into one another. Atomic theory is credited to John Dalton. Dalton's atomic theory states that all matter is composed of atoms. Atoms cannot be made or destroyed. All atoms of the same element are identical. Different elements have different types of atoms. Atoms of two or more elements combine to form chemical compounds. In fact, Dalton had proposed atomic theory to explain the law of definite proportions and the law of multiple proportions, which are obeyed by elements when they combine to form compounds. The law of definite proportions states a given compound always contains the same proportion of elements by mass. For example, consider a water molecule. The ratio of the mass of oxygen, MO, to the mass of hydrogen, MH, in a water molecule is always fixed and is independent of how the water molecule is formed. The law of multiple proportions states that when two elements are combined to form more than one compound, then, for a fixed mass of one element, the masses of the other elements in different compounds are in the ratio of small integers. For example, carbon and oxygen combine to form two compounds, carbon monoxide and carbon dioxide. If M1 is the mass of oxygen that combines with M units of carbon in the carbon monoxide, and M2 is the mass of oxygen that combines with M units of carbon in carbon dioxide, then, according to the law of multiple proportions, the ratio M1 is to M2 is a simple ratio of small integers. Dalton's atomic theory, when combined with Avogadro's law, helps explain Gay-Lussac's law. Gay-Lussac's law states that when two or more gases combine chemically to form another gas, then the ratio of volumes of the gases are in the ratio of small integers. And Avogadro's law states that at constant temperature and pressure, equal volumes of all gases contain the same number of molecules. An interesting thing to note here is that Dalton's atomic theory is also known as the molecular theory of matter, as the elements are often found in the form of molecules. Generally, the size of an atom is about an angstrom unit, which is equal to 10 raised to the power minus 10 m. In solids, the interatomic separation is very small, approximately 2 angstrom, whereas in liquids, the atoms are separated by 2 angstrom, but the atoms of liquids are less rigid than those of solids, and hence the liquid can flow. Whereas, in gases, the interatomic separation is very large, approximately 10 angstrom. In solids, the atoms are tightly packed. That is, the interatomic force is strong. In liquids, the atoms are loosely packed. That is, the interatomic force is weak. Whereas, in gases, atoms are very loosely packed. That is, the interatomic force is negligible. Due to interatomic forces, solids have a definite size, shape, and volume. Liquids have definite volume but no definite size and shape, and gases have neither fixed volume nor definite size and shape. The molecules and atoms of matter can be seen through electron microscopes and scanning tunneling microscopes. So we now know that atoms are divisible and are not elementary. An atom is made up of a nucleus in the center and electrons revolving in orbits around the nucleus. Protons and neutrons together make up the nucleus of an atom. These protons and neutrons are further made up of quarks. It is believed that quarks may be further made up of string-like elementary entities. In case of gases, interaction between molecules is negligible, except during a collision because the molecules are far away from each other. So, it is easier to study properties of gases such as pressure, temperature, and volume compared to that of solids and liquids. Gases at low pressure and high temperature satisfy a simple relation. PV is equal to kT, where P is the pressure, V is the volume, T is the temperature in Kelvin scale, and K is the proportionality constant. Let this be equation 1. For a given sample of gas, K is constant and can be written as K is equal to N multiplied by Kb, where N is the number of molecules in the given sample. From observation during various experiments, it is clear that the value of Kb is constant for all gases and is called the Boltzmann constant. Its value is 1.38 into 10 raised to the power minus 23 joules per Kelvin. Substituting the value K is equal to NKB in equation 1, PV is equal to KT. We get PV is equal to NKBT. Let this be equation 2. We know that 1 mole of gas contains an Avogadro number of molecules denoted by Na. So, N is equal to N into Na, where N is the number of moles of the gas present. Substituting the equation N is equal to N into Na in equation 2, PV is equal to NKBT. We get PV is equal to N Na into KBT. Upon rewriting the terms of the equation, we get PV is equal to N into NaKB into T, which can be written as PV is equal to nRT. Let this be equation 3. In equation 3, R is equal to Na into Kb is called the universal gas constant. The value of R is 8.314 joules per mole per Kelvin. This value is constant for a given system of units. Equation 3 is also called the ideal gas equation. A gas that satisfies the ideal gas equation at all temperatures and pressures is defined as an ideal gas. The concept of an ideal gas is merely a theoretical concept. In practice, there is no ideal gas. If we plot a graph by taking pressure on the x-axis and PV by NT on the y-axis, the graph is a straight line parallel to the x-axis for an ideal gas. That is, the value PV by NT is constant even when pressure changes. The behavior of a real gas at 3 different temperatures is shown in the figure. From the graph, it is clear that all the curves approach the behavior of an ideal gas at low pressure and high temperature. This is because at high temperatures and low pressures, the molecules of the gas are far apart and interaction between the molecules is negligible. From the ideal gas equation, we can say that at constant temperature and pressure, equal volumes of different gases contain an equal number of molecules. That means for an ideal gas, V by N is constant. This is called Avogadro's law. Let V1 and V2 be the volumes of a gas and N1 and N2 be the number of moles of the gas. If they are at the same pressure and temperature, according to Avogadro's law, V1 by N1 is equal to V2 by N2. 1 mole of any gas can occupy a volume of 22.4 liters at STP, and it contains Avogadro's number of molecules, that is 6.02 into 10 raised to power 23 molecules. The mass of 22.4 liters of any gas at STP is equal to its molecular weight. Thus, the number of moles in a gas is calculated by using the formula number of moles N is equal to the weight of the gas in grams divided by its molecular weight in grams. As the mass of a given gas M increases, the number of molecules N also increases. That is, M is directly proportional to N. A mass of 1 mole of a gas is called molar mass, denoted by M0. It contains an Avogadro number of molecules, denoted by Na. Then, M divided by M0 is equal to N divided by Na. If the number of moles and temperature is constant in the ideal gas equation, then PV is constant. That is, for a given mass of gas at a constant temperature, pressure is inversely proportional to its volume. This is called Boyle's law. According to Boyle's law, the graph between pressure versus volume is shown in the figure. Boyle's law is also satisfied at high temperatures and low pressures. If the number of moles and pressure of a given gas are kept constant, then the ideal gas equation can be modified as volume of a gas is directly proportional to its absolute temperature. That is, V is proportional to T, and V divided by T is constant. This is called Charles' law. If we plot a graph by taking volume on the x-axis and temperature on the y-axis at 3 different constant pressures, the graphs are as shown in the figure. In this case too, the graph is well fitted at high temperature. That is, a straight line, but it is a curved line at low temperatures. This is according to Charles' law. Consider a mixture of non-interactive gases in a container. At a constant temperature T, pressure P, and volume V. Let N1 be the number of moles of the first gas, N2 the number of moles of the second gas, and N3 the number of moles of the third gas, etc. Then the equation of state for the mixture of the gas is PV is equal to N1 plus N2 plus N3 and so on into RT. Let this be equation 4. But if we apply the ideal gas equation to the individual gases, we get P1V is equal to N1 RT, P2V is equal to N2 RT, P3V is equal to N3 RT, and so on. Then N1 is equal to P1V by RT. N2 is equal to P2V by RT. N3 is equal to P3V by RT, and so on. Substituting the values of N1, N2, N3 in equation 4, we get PV is equal to P1V by RT plus P2V by RT plus P3V by RT plus so on into RT. On simplification, we get P is equal to P1 plus P2 plus P3 and so on. That is, the total pressure of the mixture of gases is equal to the sum of individual partial pressures exerted by all the gases. This is called Dalton's law of partial pressures. From the microscopic point of view, an ideal gas is defined by making the following assumptions based on the kinetic theory of gases. The postulates are: a gas consists of a large number of small particles called molecules. The number of molecules are of the order of Avogadro's number. The molecules are in constant random motion and obey Newton's laws of motion. The rapidly moving particles constantly collide with one another and with the walls of the container. All these collisions are elastic and of negligible duration. That is, in the collisions between the molecules and the walls, the total momentum and the total kinetic energy are conserved. The interaction between the molecules is negligible except during a collision. That is, the intermolecular forces are negligible because the average distance between the molecules is large compared to the size of the molecules at ordinary temperature and pressure. It is also assumed that the volume of the molecules is negligible compared with the volume of the container, and the molecules are perfectly spherical and elastic. Now, let's derive an expression for the pressure of an ideal gas based on kinetic theory. Let us consider a gas in a cubical vessel with the length of a side L, and the walls of the vessel perfectly elastic. Take the X, Y, and Z axis to be parallel to the sides of the cube, and call the faces perpendicular to the X-axis A1 and A2. The area of each face is equal to L square. These two faces are parallel to each other. Consider a molecule in motion and assume that its velocity along the x-axis is Vx. If this particle collides with face A1, since all the collisions are elastic, it rebounds with the same speed in the opposite direction. Let the mass of a molecule be m. Then the initial momentum of the molecule along the x-axis, pi, is equal to mvx. The final momentum of the molecule along the x-axis, pf, is equal to m into minus vx. Or the final momentum of the molecule along the x-axis, pf, is equal to minus mvx. Therefore, the change in the momentum of the molecule is delta p is equal to final momentum, pf, minus initial momentum, pi. That is, delta p is equal to minus mvx minus mvx. Thus, delta p is equal to minus 2mvx. As the collision is elastic and momentum remains conserved, the momentum imparted to the wall of the cube for one collision, delta p dash, is equal to 2mvx. Let this be equation 1. If the molecule travels with a constant velocity minus vx along the x-axis and without any collision with the other molecules reaches face A2, then the displacement of the molecule along the x-axis, that is, the distance between faces A1 and A2, is L. Then the time taken to travel from A1 to A2 is equal to L divided by Vx. The molecule, after colliding with face A2, rebounds and travels towards A1 with a constant velocity component Vx along the x-axis. The time taken to travel from A2 to A1 is also equal to L divided by Vx. Assuming that there is no collision with the other molecules, the time interval between two successive collisions of a molecule with phase A1 is delta T is equal to 2L divided by Vx. Then the number of collisions of this molecule per unit time is C is equal to 1 by delta T, which is equal to Vx by 2L. The total momentum imparted per unit time to phase A1 with this molecule is equal to C into delta P dash. According to Newton's second law of motion, the total momentum imparted per unit time is equal to the force exerted on phase A1 due to this molecule. Therefore, the force exerted by one molecule delta F is equal to C into delta P dash. The force due to this molecule is Vx by 2L into 2mVx, which is equal to mVx square by L. As there is no preferred direction of velocity of the molecules in the vessel, the motion along any one of the three axes is Vx square is equal to Vy square is equal to Vz square is equal to 1 by 3 into Vx square plus Vy square plus Vz square, which is equal to 1 by 3V square. So the force due to this molecule is delta F is equal to 1 by 3 mv square by L. Let the given sample of gas contain n number of molecules. Then, the mass of the total gas is equal to the mass of one molecule, m, multiplied by the total number of molecules, n. The average square velocity of all the molecules of the gas is equal to the sum of the square of the velocities of individual molecules divided by the total number of molecules, that is, V square bar is equal to V1 square plus V2 square plus so on plus Vn square the whole by n, which is equal to sigma V square by n. Then the total force exerted on the face due to the total molecules is sigma delta F, which is equal to sigma 1 by 3 mv square by L, equal to 1 by 3 m by L into sigma v square. Multiplying both numerator and denominator by n, we get F is equal to 1 by 3 mn by L into sigma v square by n. Pressure is defined as force per unit area. Pressure acting on face A1 is equal to force divided by area of face A1. By substituting the value of force in the equation for pressure, we get pressure is equal to 1 by 3 mn by L cube into sigma v square by n. Simplifying, we get pressure is equal to 1 by 3 mn v square bar by L cube, where v square bar is the average of the square of the velocities of the molecules, average of v square, and n by L cube is the number of molecules per unit volume, known as the number density denoted by the capital letter N, and v square bar is the average of v square. From the kinetic theory of gases, the pressure exerted by a gas is equal to 1 by 3 mn v square. The expression for pressure exerted by a gas has been calculated by taking a cubical container. The expression is true for a container of any shape, because in the final expression, the terms representing the area A and time delta t are not present. While deriving the expression for pressure, we have not considered the collisions among the molecules. If, due to collision, the velocity of the molecule changes, there will always be a molecule that acquires the same velocity as that of the molecule under consideration. Overall, molecular collisions will not affect the above calculation.